if P of t is the size of a population at time t, which of the following differential equations describes linear growth in the size of the population? So what we need to find is which one of these differential equations, which all seem to give us the value of the first derivative of the population, gives us a differential equation that describes a population that is growing linearly. So P of t is the function of the population in terms of time. And if we want to find out which one of these differential equations describes a linear growth in the size of the population, we need our P of t to be linearly dependent on the time. So that means the form of of P of t is going to look like some slope, we'll say m times t plus some value, some constant that's like the y-intercept. So what we really need is P of t to be a linear equation of the form y equals mx plus b, where the independent variable, in this case it's time t, has a power of just 1. So this is linear growth in the population. And if we were to take the derivative of this, so the derivative with respect to time of p, or really this is just dp dt, you can write it as either ways, then the derivative would just look like some constant, which would be the slope. Because this is this linear equation here that we want P of t to look like has an exponent of 1. So when we subtract 1, it just becomes a 0 exponent, and that gets rid of the t term. And any constants are also just become 0 when we take the derivative. So that means what we're looking for is the first derivative of the population to just equal some constant. There should be no t's in the equation or any p's. It just the derivative just needs to equal a constant. And if we look at all of these answer choices, the only one that does that is answer choice A, where the first derivative of the population is just equal to some constant. The others, if we look at them, they have some t's in them or some p's. Obviously, we can rule out the p's because the function population is dependent on only t. It doesn't vary with respect to p. And if our first derivative have any t's in them, that means when we take the integral to go back to the P of t equation, we're going to have like t squared or even t cubed in the case when t is squared. But we don't want t to have an exponent greater than 1. We want it to be a linear equation. So t has to have an exponent of 1. So we can also just rule out B and C. So A is the only one that describes linear growth in the population because its derivative is just a constant.